What is common between bacteria in a petri dish? The spread of viruses, nuclear bombs, the decay of nuclear waste, compound interest, the rates of chemical reactions, and financial mod. The answer is this function in this one letter. Okay, let's do it. To understand the importance of this one letter to mathematics, we have to understand two things. The first is exponential growth, and the second is the natural exponential, which is what E is. But before that, a quick summary. The letter E in mathematics is an irrational number, meaning that the decimals are never ending and never repeat and go on forever. You may know another such number, pi, which is half the circumference or the area of a circle with the radius 1, also known as a unit circle. The proof for why E is really complicated and kind of not necessary for this video. What is more important for this video is understanding why E is so damn important. First, let's understand what exponential growth really means. In nature, we observe a lot of patterns and trends, and humans like to interpret those trends. One such trend that was observed was when it came to growth and decay, and the trend was quite common in, let us say that I have 1 cent, and every year the government gives me as many cents as I have that year. So the first year I get 1 cent, so now I have 2 cents. The next year I get 2 more, so now I have 4, and then I get 4 more, and then I have 8. And oh my god! Not only is my wealth increasing, but the rate at which my wealth is increasing is also increasing. And it's not just wealth and finances. This pattern was observed everywhere. From bacterial and fungal models to the spoiling of food to how diseases spread in society to even the spread of fires. It was like this pattern was ingrained in nature and in human society. Someone had to decode it. So it's pronounced, as a friend of mine always says, it's pronounced Euler, not Euler, making contributions in multiple fields of mathematics, from calculus and geometry to mechanics and number theory and many more. Which let us just appreciate for a second the genius of this man. When you talk about genius, we say like Einstein, Newton, Darwin. Like, give the man some credit. You know what? Let's give some love to Leonhard Euler. Great prodigy from Basel decided to take a stab at the problem of exponential growth. He used the ideas of calculus to lay down the basic definition of this kind of growth. Now, before you get scared, it is actually not that complicated and like not that crazy. It's actually pretty simple. I'll just explain it in simple terms. He used the idea of a simple derivative to model the exponential function. Now, what a derivative is kind of like a slope to a function, but like at one particular point. It's called the instantaneous rate of change, which is like, I know it sounds like kind of counterintuitive, but like, think of it this way. Think of a slope where the 2 points that you're taking the slope between get smaller and smaller and smaller until they're like infinitesimally small. Basically, like how much y changes for like a very small change in x. That's basically what a derivative is. It's like the rate of change for an infinitesimally small change. Now, how Euler defined the function is quite simple and straightforward. The idea is that the derivative of a quantity is proportional to the value of that quantity. However, that naturally raises a question when you bring the idea of proportion into the table. You're saying that the change in quantity per unit is dependent on the value of the quantity itself. So, is there a natural exponential? An exponential so intrinsic to nature that the rate of change of the exponential property is equal to the exponential property itself. That function was also found by Euler. Surprise, surprise. And the function is f of x equals e to the x. The derivative of this function is also e to the x. And there we have it, e in all its glory. In honor of the mathematician, e is now known as Euler's constant, one of his many prolific mathematical discoveries. But hold on, this is just one base for an exponential function. Why does it apply to every exponential function? This is where we can go back to a neat trick that we learned in school. You may remember one of the rules of exponents, where if there's like an exponent such as a to the b and you raise the whole exponent to another exponent c, the exponents just multiply. It becomes a to the b c. Or we can say that when an exponent is raised to another power, the exponents just multiply. This is because when we raise an exponent to another power, we are multiplying that exponent that many times, so all of them add up, so both the exponents end up multiplying. And that addition is due to the property that when you take something to an exponent, you multiply it that many times. So if you multiply two exponents with the same base, you're basically multiplying it that many number of times, so you get the exponent. But how is this relevant to e exactly? Well, we can do a neat trick where we can take a common exponential, such as let's say 2 to the x, and express it as e to some power to the x. This would be an equivalent formulation, and we would get the same result exactly. But how would we know what power to use? This is where the natural logarithm comes in, which tells us to what power we need to raise e to get a certain number. So we can express 2 as e to the ln 2x. Yes, that's what ln means. What's the use of this though? Well, remember the defining property of an exponential function. As the rate of change, the derivative, is proportional to the quantity itself, we can find this proportionality constant very easily when we standardize the function using e. How do we do that? Well, we can see that by taking the derivative of the function. This involves a bit of calculus, but it's just formula. Let us assume the base of a certain function is e squared. If that is the case, we can express it. So this derivative just comes out to e to the 2x ln e squared. Because of logarithmic rules, this just becomes e to the 2x ln 2 ln e, and ln e is just 1. So this just becomes ln 2 e to the 2x, and now we have the proportionality constant ln 2, and that is why e is so important. It allows us to express every exponential function with that proportionality that we discussed earlier, with the rate of change or the derivative is proportional to the value of the quantity itself. As such, this irrational number became the very basis of every single pattern in nature that exhibited this very common trend. Euler's constant and its unique properties are forever immortalized in mathematics, and their usefulness in modeling everything from the spread of diseases like COVID and the decay of nuclear waste to compound interest in finance can all be attributed to one genius prodigy from Basel, Switzerland, and his little number e. Thank you.